Welcome back to our YouTube channel. This is your ADC Max. In this video, I am going to introduce two familiar named theorems in Z transforms. Then I have already seen that the same types of theorems in the Laplace transform as well. So what are the two theorems? Let us see that initial value theorem, final value theorem. What is the Z transform of the signals f of t? The minimum value is 0 for n, the maximum is infinity. So n equal to 0, that is the t tends to 0, f of 0, that is called the initial value theorem. The value for f of 0 is limit z tends to infinity f of z. What's f of z? Is the transform of f of t. What's the final value theorem? Final value is maximum value. What's the maximum value for t? Infinity. So what's the f of infinity? So f of 0 means initial value, minimum value. F of infinity means final value, f of infinity. So final value theorem is nothing but limit z tends to 1, z minus 1 to f of z. Z minus 1, z minus 1, z tends to 1, f of z. So I am going to derive the final value theorem first, then I move on to the initial value theorem, because initial value theorem is which we get just with the help of the definition we will get the answer. So I go for the final value theorem. Final value theorem, what is final value theorem? Yeah, I start with the, I think I need z minus 1. So I start from f of t plus t where k equal to 1, because already we know the shifting property is there. What's the z transform of f of n plus k into t? Yeah, already we know. When k equal to 1, we get the second shifting property. There is nothing but z transform of f of t plus capital T is equal to z into f of z minus f of 0. So with the help of this result only I am going to derive this in final value theorem. So z transform of f of t plus capital T minus f of t is equal to, by the definition replace the small t by capital N t, small t by capital N t, then z power minus n stands from 0 to infinity. Now by using the linear property, this can be known as z transform of f of t plus t minus z transform of f of t. What is z transform of f of t? F of z. Okay. What's the z transform of f of t plus t? That's why I told you that by second shifting property is z into f of z minus f of 0. Now this can be rewritten. This term can be rewritten z into f of z minus f of 0, and this is the f of z is equal to the same is limit z sigma equal to 0 to infinity f of n t plus t minus f of n t z power minus n. Now taking the limit z tends to 1, because it's final value theorem, limit z tends to 1. For initial value theorem, limit z tends to infinity. That's it. Z tends to 1, and both sides what happen? On both sides what we will get? So limit z tends to 1. By combining these two terms, we get z minus 1 f of z, because f of z is common, minus z into f of 0. On the right hand side, limit z tends to 1, sigma n equal to 0 to infinity f of nt plus t minus f of nt into z power minus n. Right? Now putting z equal to 1, what happened this side? Let's see that this is equal to, this is equal to. The left hand side becomes limit z tends to 1, z minus 1 into f of z minus, by putting z equal to 1 we get is f of 0. In the right hand side, by putting z equal to 1, this becomes 1 power minus n. Also 1 power minus n is 1 is no problem. So this comes simply sigma n equal to 0 to infinity f of nt plus t minus f of nt. Now I want to just substitute n equal to 0. We substitute n equal to 0 here, what happens? We get is f of t, correct? Minus, by putting n equal to 0, we get f of 0. Is right? Right? By putting n equal to 1, I am getting that it is f of n equal to 1. So 1t. So it is nt. 1t means t plus t is 2t minus, by putting n equal to 1, we get f of t. By putting n equal to 3, we get, continue like that. So by putting n equal to 2, we get 2 plus 1, 3. So f of 3t minus f of 2t. So continue like that. Finally what we will get? We will get it is up to infinity. Up to infinity into z power minus 1 is 1 is already over, no problem. So what about the f of infinity, that is n plus 1, n t minus n plus 1t. So this coming like that, f of infinity minus as k tends to infinity, f of n plus 1t minus f of nt. F of n plus 1t, that is the general term. That is the general term. So it is going on like that. It is going on up to infinity. F of n plus 1 into t minus f of nt. Okay. As n tends to infinity, what happened? As n tends to infinity, everything becomes infinity. So before going with that, can you see that this f of t get cancelled, f of t get cancelled, f of 2t get cancelled, f of 2t get, so f of 3t get cancelled. So continue that, everything is get cancelled. Everything is get cancelled except the last term and the first term. What's the last term? As n tends to infinity, we get this f of infinity. As n tends to infinity, we get f of infinity. Because you see that every term get cancelled. F of t, f of t get cancelled. F of 2t, f of 2t, f of 3t, 3t, etc., etc. Everything get cancelled. As the last term is infinity, is the term. Infinity plus 1 is infinity only. So f of infinity. And still we have this term f of infinity in the this f of 0. In the left hand side, what happened? The left hand side is also limit z tends to 1, z minus 1 into f of z is there, no problem, minus f of 0. So by combining these two, is equating both the sides, what we will get? We will get f of 0 will cancel. So what's f of 0 will cancel means the rest is limit z tends to 1, z minus 1 f of z is equal to f of infinity. That is nothing but the final value theorem. Final value theorem. So here by putting z tends to 1, this becomes power 1. This becomes 1 power minus n is cancelled. But after expansion, except the initial value and the final value, it will be retained. In between the terms, everything get cancelled. That's why I am showing you that t get cancelled, 2t get cancelled, 3t get cancelled. So it is coming like that. So excluding the first and the initial value t equal to 0 and the final value, that is infinity, f of infinity, both are remain same because f of infinity minus f of 0. So after cancellation of f of 0 from both the sides, we get the final value theorem. Now what about the initial value theorem? Then f of 0 limit z tends to infinity f of z. So now I am going to prove the initial value theorem. Let us see that initial value theorem is very simple. Let us see the proof of initial value theorem. As we know that what is the f of z? F of z is equal to z transform of f of t, or otherwise by the definition is sigma n is equal to 0 to infinity f of n capital T z power minus n. Is right? Is right? Now, if I take n equal to 0, n equal to 1, n equal to 2, what we will get? We will get when n equal to 0, this will use f of 0 z power minus 0. N equal to 1, we get f of t z power minus 1. N equal to 2, we get f of 2t z power minus 2 plus etc., etc. up to infinity. So for the initial value theorem, take limit z tends to infinity. For the final value theorem, we took limit z tends to 1. So that's the concept. So for the initial value theorem, what's left hand side? The left hand side is f of z. Now taking limit z tends to infinity. Taking limit z tends to infinity on both sides, what we will get? On both sides, we get the left hand side is limit z tends to infinity f of z is equal to right hand side is limit z tends to infinity f of 0 minus f of t by z, because power minus 1 is coming, the denominator is plus power, by z square minus etc., etc., plus etc., etc., f of 0. Now by taking the z tends to infinity, what we will get? There is no z term, so this is retained here f of 0. If it is z tends to infinity, anything by infinity is 0, anything by infinity is 0. So everything is 0 except the first term. So that is the initial value theorem. Limit z tends to infinity, f of z equal to f of 0. Otherwise, f of 0 is equal to limit z tends to infinity, f of z. That is the initial value theorem. So this is the simple proof of the initial value theorem and the final value theorem. Now, what are the applications of these two theorems? Let us see a simple problem. Let us find out some interesting problems based on the initial and final value theorem. Let us see the few examples based on the initial and final value theorem. The main idea is we doesn't know what will be the f of t. We don't know what is the input f of t. Only we have the output. Once we have the output, what will be the initial value, what will be the final value, we can easily find out. So that's the beauty of this theorem, initial and final value theorem. I have the output only, but I don't know the input. What is the f of t? But what is the initial value, f of 0? Similarly, what is the final value f of infinity? So there are two problems for your easy understanding. The first one, f of 0. So by initial value theorem, so we don't know the f of t, but even though we can easily find out this value, by initial value theorem, what is f of 0 stands for? It is limit z tends to infinity f of z. Now this time f of z is z into z minus cos 80 by z square minus 2z cos 80 plus 1. So can you substitute z tends to infinity directly? We get infinity by infinity. It becomes undefined. So this contradiction to the given input. So what we are going to do that? Take the z outside. So z square minus 1 is 1 minus cos 80 by z. So take the z outside before applying the infinity. Taking the z square from the denominator as well, minus 2 cos 80 by z plus 1 by z square. So once I repeat this step, cancel the z term, how much is possible, then apply the limit. That's the case. By taking z outside, so z square minus 1 minus cos 80 by t z square outside, so 1 minus 2, z get cancelled, 1 z get cancelled, so 1 z retained in the denominator, and 1 by z square. Now let us cancellation of z square. Now apply z tends to infinity. Anything by infinity? 0. So this term becomes 0. Anything by infinity? 0. Anything by infinity? 0. So 1 by 1, the answer is 1. Very simple. But I don't know what will be the input. I don't know what's the input f of t, but I have the output so that I can easily find out the f of 0 value. So this is the real application of the initial value theorem. What about the second sum? The second sum is 10z by z square minus 3z plus 2. The same case, the same idea. So when I am going to use the f of z, 10z, what's the f of 0? By using the initial value theorem, it is 10z by z squared minus 3z plus 2. So if you apply directly infinity here, infinity by infinity is infinity only. So there is a contradiction. So we don't do like that. So what we are going to do then? Substitute before applying the limit, cancel the z term. So in the numerator, 10z only. So don't bother about it. In the right hand side, there is the left hand, there is the numerator. Taking z squared is outside. Z squared is outside. What will we get? We get 1 minus 3 by z plus 2 by z squared. Is right? Now cancel the z here. I think so. Unfortunately, we have one more z in the denominator. So limit z tends to infinity, 10 by z into 1 minus 3 by z plus 2 by z. So even though when we substitute z tends to infinity here, 3 by infinity is 0, 2 by infinity is 0. This is 1, no problem. But here, infinity. So 10 by infinity, anything by infinity is 0. So the answer is 0 for the f of 0. What about the f of infinity? For the f of infinity, use the final value theorem. Use the final value theorem to get the f of infinity. So by final value theorem, what we get? F of infinity is equal to limit z tends to 1, z minus 1 into f of z. What's f of z here? I think so. 10z by z squared minus 3z plus 2. So substitute z equal to 1. If you substitute z equal to 1, 1 minus 1, 0. 0 nothing 0. You get the 0. But what I suggest you that better you can take z, cancel, then apply the limit, will get the answer. That's the best idea. So what I suggest you that before going to that, I can rewrite the denominator of the given function f of z is 10z by, I think so it is a product of two linear factors z minus 1 and z minus 2. Z minus 1 and z minus 2. So after cancellation of z minus 1 and z minus 2, we'll get it is limit z tends to 1, 10z by z minus 2. So the same idea, what we done here, we try to cancel the z term, but here it is possible to try to cancel the linear factors. We can make it the linear factor in the denominator, cancel it if possible. Then z minus 1 z will cancel. Now putting z equal to 1, we get is 10 in the numerator, denominator is 1 minus 2. 1 minus 2 is minus 1, so the answer is minus 10. Suppose you are directly using z equal to 1 here, 1 minus 1 0, so 0 nothing 0, but that is a wrong idea. Try to cancel the z minus 1. This looks like the Cauchy's residue theorem model. When how to get the residue of f of z at the pole z equal to a, the corresponding pole term will cancel. The same concept here, z minus 1 get cancelled. Then apply the limit, you will get the answer. This is minus 10. So this is the application of the initial and the final value theorem. Initial and the final value theorem. I hope everyone please understand this concept. Please go and subscribe. Recommend to friends our ADC Max YouTube channel. Thank you for your support. Take care. Bye.